Hello, everyone. Thanks for coming to this week's RISE seminar. Our guest speaker this week is Dr. Andy Feng. Uh, he's currently at Nvidia. He has a long and storied career in a lot of very exciting Silicon Valley and technology companies in architecture. He received his PhD from Osaka University in Japan, and since then has been at, as I said, many exciting companies, including Xerox, Netscape, Yahoo, and now at Nvidia. Nvidia is definitely one of the more exciting companies these days, with a lot of hot buzz and exciting things happening. And we're all very excited to hear what Andy's doing to help sort of, accelerate a lot of today's groundbreaking AI and other research. So without further ado, let's welcome Dr. Andy Feng.
No, wait, here. Can you guys see my screen?
Yes.
Hi, everyone. This is Andy Feng here from Nvidia. And today with my co-worker, Samir and Daguan, we are honored to share some of our work we are doing at Nvidia to accelerate the machine learning pipelines. So during the call, if you guys have any questions, please use the Slack channel to raise your questions. So hopefully Samir and Daguan could address many of them.
I think the Zoom chat would.
Yeah. So the way I like to, we started with the introduction about the big lands in the context that we are operating on, and then we will zoom into one particular vertical, that's medical side for the AI stuff. And then after that, we will talk about some horizontal effort NVIDIA doing and to accelerate the Spark side of the work. And then we will wrap it up with some of the challenges we wish be able to overcome in coming, in the near future. So, okay, so as an introduction, I would just make sure everybody on the same page. And we are in the very exciting time with the significant of the data growth in all those different areas, with the enterprise side, or with the voice, IoT side, or with the social media, web, and the sensor, everything, right? If you see the last, a few years, the amount of data we are introducing through all of the different channels is really growing very rapidly. As some of you realize, data is our new oil. And as a result, like a lot of interesting opportunities are being identified in various verticals. For example, in the healthcare side, in the lot of recent work in the medical imaging side of research is doing AI with those data, right? And then now you have more and over hundreds of the AI-based applications that has cleared FDA approvals, right? So those are just examples of how those data is enabling all those new set of the applications to help to make our life better. And certainly if you look in the IoT side, there's a significant business opportunities. And then you see, and more hospitals are getting smarter over times, right? So then with all those opportunities with us, then it will be interesting to know is what's the thing going to enable us to address those opportunities. And here is one slide I would love to share, that it was from Lice Lab or from the AMP Lab graduates, Leonard, and that he was shared at the Spark AI Summit this year. So it is interesting to see how the underlying information technology has been evolved in the last 10 years. For example, with the storage side, like started from the speed of the access of the storage technologies in the last 10 years has been like almost every 5 years, 10x speed up has been seen. Similarly, in the networking side, have the similar speed up we are seeing. And then on the other hand, like in the CPU side, we visit all the cloud, and we have many of us have the easy access to a lot of the computation, clusters. And they are tended to be very easy to access. On the other hand, if you look into the cloud speed point of view of the CPUs, it is a little bit unfortunate to see that we are hitting some bottleneck, right? In the last 10 years, logically, we have not seen much growth in the CPU cloud speed. So that in some ways is the opportunities. So on the other hand, I would love to share to bring you to the attention to the speed up we have seen in the GPU side. So this slide here is about the speed up in the latest set of the GPU device, GPU Nvidia has introduced in the last 4 years. If this number here is based on a benchmark of the 10, a combination of the 10 benchmark applications. So logically, in the last 4 years, we are seeing 9x, from an application point of view, 9x speed up in 4 years, right? So with that, to enable those, I think we have been introducing all the different, the GPU technologies. So then in general, I think it's all believed from Nvidia. We believe it's the new set of the, computing technologies like GPU going to will be empower very large number of applications, like from the the movies, the video, game, data centers, lot of AI applications, or computation on the edge like 5G, or with the automobile, self-driving cars or robotics, and many, all of them going to be empowered by, the new technologies that we are bringing into the market. Then the one interesting approach Nvidia is taking, we are taking a full stack approach. One hand, we are known with our GPU, set up the GPU, we are keeping introducing into the market. On the other hand, I wanted to bring attention to, like, for example, we have been also bringing a whole systems. For example, we have been doing, I think this is, I think the picture here is the DGX, and that was the original, main was designed for the AI, we bring like 8 or 16 of the GPUs into a single board in a system that enable you to do a very advanced AI development. On the other hand, we have the system for the edge or the embedded devices. So that is the kind of the system hardware side of the things. On the other hand, really, Nvidia and more is in the software business. So we are working, we are building a set of the platforms, and whether that is the horizontals or the vertical side. We wanted to make it really easy, try to reduce the barriers to adopt our technology and to enable our users to do a good job in their, to address their business needs. What's going on here? Look like I'm going backward. So as you could imagine, so this talk here, I want to mainly focus on the machine learning pipelines And if you're thinking about it, right, NVIDIA is known to be our GPUs is known to be, really good for the AI model trainings. And then many of you, when you do the AI, you're using the TensorFlow, PyTorch, all those things, and then many times you are using the GPU to the model training. And then recently, I think we have been expanded to many other places like AI inference, model inference, and I think that's kind of the relatively known in those area. And I think the other side, for example, we realize in some of the verticals, it's really hard to create the training data. So as a result, we have been introducing the annotation technologies building on top of our AI thing, capabilities. And even recently, we realized that, even beyond AI, right, a lot of the computation in the data center is doing the data analytics. So it's our desire to even make the data analytics type of workload also really getting significant speed up with our technologies. So that is the logic, the context. I wanted to give you some examples, how exactly we are trying to help out. Does it make sense? Okay, yeah. So the first thing, let me look into, let's take a peek into our healthcare verticals and focus on how we try to enable the AI in the medical area, right? So one of the examples I want to mention here is our recent effort working with the partners on the COVID trial. So logically, what we wanted to do with the COVID situation going on, many of the hospitals, try to, when a patient come to your hospital, so in some way, during that process, one wanted to figure out if the hospital needed to make an interesting decision for this patient to say how severe this patient may have these COVID problems. The particular problem we tried to work on was to say, whether in the 24 hours or 72 hours, whether a given patient he may need to have we needed to give some oxygen level support here or not. Right. So with that, I think there was we have a partner in Mass General Journal in Boston has been working on interesting deep learning models outlined here. So what they're doing is taking the X-ray images together with the medical recorded information of the patient. And then you're going through this deep learning, like logically, it's this portion of the deep learning network. First, they're using the ResNet to get the X-ray related features, and then have another portion of the network combine the X-ray features together with the medical reported information to do the prediction about for a user. So this is so this is a thing we try to do, but the problem is, from the Mass General point of view, they have a limited amount of data for the COVID from their set of the hospitals they have. So as a result, it's really hard for them to make the model accurate, or even harder to make the model useful, outside, in the world in general, right? So what we have been doing with the Mass Journal and others in the last several weeks, we have applying a federated learning approach. And we are partnered up with 20 hospitals globally. About half of them are in North America, right? There was Toronto Mass General Hospital and some hospital in New York and NIH and Children's Nationals in DC, and West Coast here, and together, and then we also have the hospitals from Brazil, UK, Taiwan, Japan, and South Korea. So this is also so obviously by when we do the federated learning here. So the reason we did the federated learning is to say because we are, as I mentioned earlier on, in the model itself needed to use the medical information, right? So also the medical information is very much private. So we want to make sure no data is shared or leaked across sites. So by applying NVIDIA technology called Clara, what the team were able to achieve within about 3 weeks, be able to produce a model of accuracy 0.94. And then it's even more interesting is that the model is quite, compared with the model that, any model, created from those local data sets by all the users, all those sites. We see in average, we are seeing 38% improvement for generalizabilities. What does that mean? The model we are producing here, I think partially because you have all the data from the different hospitals. As a result, we'll be able to have a model, very easily applicable for very different hospitals. As I mentioned, that is in order to do those, so we say, you need to have some software to do the job. By the way, to apply the federated learning approach across this global, we believe this is maybe the first in the, in our field. So then what does that enable them to do is the set of the software we have. So that in NVIDIA, for example, the way we have been doing is for healthcare verticals, we have developed a platform called NVIDIA Clara, right? It has the set of, tried to attack all the different areas with the imaging side, or with the genomic side, or smart hospital stuff. And then we make those software as easily available for the people to use. And if you take a slightly deeper look into the imaging point of views, we tried to cover all phases of this deep learning pipelines. Starting from, as mentioned earlier on, we found, especially for the healthcare medicals, annotation or the produce the training data is a headache. So we have been added some technology on it. Then we provide something for to enable you to train the medical models very easily. And then additionally, we have the application, deployment side of the things, and enable your things to enable the model to be embedded into medical devices. So here is, for example, as I mentioned earlier on, annotation is hard, right? So the reason was, if you think about, for the medical data, many of them are the 3Ds, right? So then in order to do the training, you needed to prepare 3Ds. For example, you wanted to indicate, what's the, which portion of your lung has the problems, right? All those things, right? And then for a particular, which portion of the portion is considered to have the tumor in your lung or brain, all those things. And in order to do that, you needed to so in most of the researchers in the medical side, they tend to rely on the public data set to do this thing, to do the training. But the public data set is a very small amount of them. And then some of the research organizations, more advanced, they tried to hire people to just sitting there day by day produce the training data. And we, one day I visited one of the very highly respected research university at the East Coast. I saw like 4 of the annotators sitting there, 80 hours a day, or 5 days a week. They keep doing this job, slice by slice, try to do the annotations for the to plot the training data. So what we thought is what Nvidia we decided to do is to say, what if we have be able to using the AI to speed up that process, because it seems to be the instead of having the annotator just doing the job with a piece of the software have no smartness at all. So as a result, we introduced this AI-assisted annotation technology inside of the Clever. As you saw in some of the example here, they could be speed up the annotation process quite significantly. Then the next, for the training side, one may wonder, why even Nvidia care about why don't they just using the TensorFlow, PyTorch, just do your job, right? And here's some of the numbers you are seeing. You could see, why if you're just using the native, some deep learning library natively, how long you're going to take to train your models. And so what we did is we did a lot of the optimizations, tried to the Clara train piece of this software stack. We did it, over the time, we did more and more optimizations to address the medical imaging specific needs. So as a result, sometimes we see, even over 50x speed up comparing with a baseline a deep learning framework. So then the other side is, it's now that you do that, and then at the beginning of our job, when Daquan's team, for example, when we did the job, many of them depend on their previous knowledge on the source task. So now these days we have introduced the auto MLs to enable the network architecture search and hyperparameter search and many others, and enable them to leverage all the the GPU resources to do to find the optimized AI models for the medical task. So we are applying a lot of new interesting things such as reinforcement learning and others. And we have seen, compared with our previous approach, and the auto ML actually has lifted up the accuracy of our models. And as I mentioned earlier on, then during the process, certainly we realized that for the healthcare, many of the institutions do not have enough data, and then they wish they have the ways unable to do the collaboration with others. On the other hand, they do not want to sharing the data. As a result, we have developed the Clever federated learning technologies. And then we are expanding that beyond healthcare into the other, such as the self-driving car and others. And then to make sure we keep moving the field ahead, and we are making many of our foundational technology as an open source. So about 6 months ago, we started an open source project called Monai, and with the collaboration of the King's College and several others. And it is an open source project focused on the healthcare AI. And it comes with the, some of the charts here just indicating, how much difference compared with the baseline PyTorch models versus the, or Monai-based solutions, how much difference it is seen by the software, open source software, we are jointly developing with many others. We hope like the lots of other organizations are jumping in, and recently, for example, we have multiple other universities, and they are researchers are make a significant contribution into this medical AI repository. And then some of the work you could are being summarized in our recent articles in Nature journals. It's they talk about some of the interesting work we believe needed to be done for the healthcare AI. So anyway, in summary, from if you could see in this the summary, a few slides we just walked through, what the Nvidia have done is tried to bring the AI or tried to make the life of this AI pipeline from the creation of the annotation to the training, all the whole step. We tried to make the life easier. As a result, we are enabling our researchers in the field to be able to achieve the set of the achievement, be able to like the such as this COVID model development. And I think we have many other verticals is very similar stories. So now with that, let me, so this is our vertical story, right? And now let's, since you guys are nice lab, so I would rather just talk. And the next few slides, I will talk about the horizontal side of the things. So we will talk about Apache Spark. And, so I'm honored to bring the Apache Spark work and the GPU together because, for into the nice lab because, Spark is from you guys. So the question here is to say, Spark has been, so it was created by the, from the MPAT lab days about 10 years ago, right? And it has been, have a very significant complexity in it. From the ground up, it was created for CPUs. So in some way, what we are taking on a mission that's unclear whether we will be able to achieve anything or not. So that's why we are, logically say, can you make this elephant moving faster or not? So here is some evidence we believe it is possible to bring GPU into the Spark, and we will make this elephant moving faster. So here is one of the benchmark we did on this one of the benchmark called the TPCS BB, and in it, so for them, so we did this benchmark in the using our so this slide here is using two DGX2 nodes. I mean, those nodes are certainly quite powerful. So as a result, you could see like comparing with let's say for this query number 5, right? Originally, you take over 25 minutes or 26 minutes or something. Now, like it take I don't know, it's about 1 minute, right? So those kind of the quite significant speed up you could be able to see with the GPUs. Now here's another one, right? So here is another benchmark with the TPCS, and then here for a particular query 37, if you see here is the for this particular test, we are running on this is on AWS. So on the AWS for the CPU side, if you take this one, quite a significant, with 8 workers on the CPU, and it's take about about closer to 30 minutes. And then with comparing with that, if you're using the GPU instance, then you reduce that to 53 seconds. Then it's interesting that if you just do the conversion to the cost, you're actually seeing is the GPU actually is saving money comparing with the CPUs. Right, almost like half of your cost here. So then some of our customers, like the Adobe, for example, they at the beginning they're not necessarily sure that's going to translate to their benefits. So but they decided to try out our technologies with their internal with their workload. So then they reported that for them, so they did both using Spark to do the ETL and the training, right? ETL and the training on it. And then again, they are saying they both, I think they're using much bigger CPU clusters, and then compared with the GPU side. But anyway, if you're looking into the cost side of the things, then again, they are, for example, if you're looking at this ETL side, they reduce about it to the original cost about 1/3. And then from the training side, this is saving even more significant, about less than 1/10 of the original cost on the CPUs. And then certainly, you could see here's another example. So they combine using the Spark to do the ETL and do the deep learning, right? And here now you see. Again, it's all the speed, both the speed up and the cost side is quite significant. Right, so the time here is get reduced from this. I think was the original code published by Facebook on the DRIM was a deep recommender system. So they have the piece of the code for the ETLs and for the training side of the things. So if you bring them down, if we we are using the we bring them onto the Spark, and then on the CPUs, and if we compare this one with the single node, single GPUs, and then you bring into 8 GPUs. And for the ETL, other stuff, you just keep and see significant improvement on it. So anyway, so what we decided to for the Sparkland, what we did was logically we decided to look into both the ETL side and the machine learning and deep learning side of the things. So that's why you're seeing also the speed up you are seeing before. So the next few slides, I think I will mainly work on so the approach we are taking here is we wanted to our GPU or the technology from Nvidia for our team and be able to adopt it by users very easy. So a few areas what we did is the first, from the foundation technology point of view, so we believe that the user should not make any code change. So let's say here is your SQL statement in your Spark job. You should not change anything in it. The only thing when you launch your Spark job, you just need to enable, to turn on a flag. Say, you want to use this piece of the accelerators from Nvidia. And the second, we wanted to enable our technologies to be able to adopt it by all those different vendors. Whether you are using the open source Spark or using the Databricks or using GCP, using AWS. And in all those areas, again, it should be very easy for you to adopt. So now you may wonder how exactly we do that, right? So the technical, what we did was we are plug our software into the Spark catalyst layers. So that is the layer got invoked by the Spark SQL data frame APIs. And so logically in it, you have, when you get in the point, eventually you're going to have set up the physical plan operations for database operations, like join, group by, those things, right? So logically, we are introducing a GPU implementation of those operators. And on the other hand, if there's a certain operator we are not supporting it, we just fall back to the existing Spark code. And then for the GPU piece of the code, then we are dependent on, we have dependent on a full stack from Nvidia. So there's a Lapis libraries that has the C++ implementations of the basic operators like join, group by within a single process. And that library is sitting on top of our CUDA libraries. So that is one side. And then the other side what we did was once you have this speed up inside the computing side, then we also wanted to have a good job to make sure your data movement between your processes is fast. So as a result, we have been working on a customized implementation of the Spark Shuffle. And this is the side of the things, if you will leverage all, the latest networking technologies and such, including the RDMA, and that will be, we leverage some of the work, called UCX. That is some of the mainly was contributed by Menonix. That is a company, a network Nvidia acquired recently. So if you look into the operator, slightly more deep into it. So let's just say here's your, here's your SQL statement, here your data frame API, right? So at the end of days, it's going to be under the cover of the Spark, is translated that to a logical plan and then eventually to a physical plan. So normally you will, in the existing code path, you will executing this physical plan into this RDD, sense, right? That is based on law-based data sets. So instead, the logic at that point, what our plugin is doing is replace that physical plan by a GPU-based physical plan. And then instead of law-based format, we are dealing with the columnar data representations of the data sets. So if you're thinking conceptually, if you, in the many cases, it's almost like a one-to-one mappings between the CPU operators and our GPU operators. And all those things just happening under the cover from the user. So, it's, so then the shuffle on the other hand, right? If you think, the shuffle was happening here is, so the Spark job is divided by a collection of the stages. And between stages, they needed to prepare, have the data move to the next stage. So normally what you do is each in the task of the previous stage, they dump the data into the disk. And from there, then the next start task happens, they pick from the disk, and doing the next stage. So what they are, the shuffle plugin we are doing now is try to minimize all those the cost of the data movement. In the ideal case, we want to, let's say your original task was running on GPU 0, and you wanted to be able to, when you say your next task is running on GPU 1, we be able to just take in the data from another GPU copied over. And then on the other hand, if we, they are sitting at different environment nodes, those things, then we be using RDMAs and our networking things to do the job. And on the other, we will try to minimize all those workload, the cost because of the data movement. So then on top of it, we are also doing some other interesting stuff. For example, one of the challenges we found out is many of the Spark users to do a user-defined functions. For example, some of them are writing those user-defined functions in Scala. Right, so here's an example, right? You are doing a select statement of this user-defined functions against a data frame. Since this data frame, this UDF function is defined, here. And then, so we tried to even make this kind of the UDF things that also work on the GPUs. So what we are doing as the early work we are disclosing in our latest release is based on compiler technologies. We are compiling this UDF into a catalyst expressions. So at the end, when you're running a job, you do not see a UDF at all. And then similarly, we are also for the users who prefer using the PiSpark UDF, we are trying to make to make sure all those things are optimized so that they minimize the data conversion cost. So anyway, so if you could see, like what we are doing here is we tried to work, this is Spark just have one example, right? What we try to do here is try to say if you are running your job for the whether you are, let's say you have a pipeline, machine learning pipeline on Spark, and we wanted to be able to speed up your pipeline from the ETL down to the to the machine learning, to deep learning, all the way. So that's why if you saw the early slides I had for the DOIM, that's why you also significantly speed up you'll be able to see. So from a user's benefits point of view, so you will see the significant speed up and also see the cost savings. Okay, now that I mentioned some of the early success in all the verticals and the horizontal platform, now let me share with you some of the ongoing challenges. So, so for the medical side, I think one of the interesting things, I think that's the two things I want to mention here. One is this AutoML. Because the medical training medical imaging training is quite complicated. And also, they are not really a known network, fit all, as a result, like AutoML is really important to helping us. Now the challenge here is to say how can you have an AutoML that is a computationally efficient. So here's how much like for the one of the experiment we did recently to achieve or to find optimized data network architectures. Like here's how much time we are spent in this phases of that search. And if you add all those numbers together, it's 100 GPU days, right? So that will be hard, right? If you're thinking about, for researchers, in Daguang's team, in Nvidia, because we have all this, supercomputers with GPU in it. So that was okay for them, or maybe okay for all researchers in Google, right? And it will be really hard for the researcher in the other side of those kind of very special settings. So it will be, so that's why I think we have been working with started some other work with the LICE lab on the AutoML side. We wanted to be able to reduce the AutoML computational cost. Then the other side of the study is the federated learning, right? And even so, in the early of my talk, I mentioned that there are success by applying federated learning for COVID. But I think in the overall, though, federated learning is still a very early stage. I would say it's a new frontier for the AI. So there's a lot of the unknowns, I think the ongoing challenges we're going to face. Like, for example, I think it's not necessarily clear, you have to deal with the, all the different institutions, you have different type of the data sets, they have different kind of devices, all those stuff. And then how you do the robust aggregations. And the same way, when you do your aggregations, and when you do your training federated learning process, it's not necessarily clear what your target, right? It is for globally optimized model, or you optimize for locally optimized models. For different tasks, you may have different objectives. And then what we have done so far is centralized aggregation models. And then we have done some early work of the cyclic federated learning as well. And then, but there's much more work needs to be done. And similarly, for example, there's a wish for thinkings in the industries to have the ImageNet type of things for medicals. And again, because it's, none of us have enough data sets to be able to do, say, here's the industry standard models with good accuracies. So we wish, be able to leverage the data sets across those many institutions. So there's a lot of significant interest to the federated evaluations of medical models. And similarly, if you're thinking about the big data side of the things, there's much work needed to be done from all angles. For example, we have been, early on, I mentioned the way how exactly we are doing for this plug the GPUs under the cover of the SQL engines. What exactly what we are doing now is a very, very naive approach, right? What we are saying is, if we are given data type, given operator, if we have the GPU implementation, let's use in GPU. But in general, you cannot say that is a smart choice. Because, if you imagine, you may need to have, because you may save some money, it's not necessary, first not necessarily clear for a given particular data size, whether your GPU is computationally effective. Even if it's computationally saving comparing with the CPUs, then you need to deal with the data transfer cost between the system and the GPU devices. And then, so as a result, I think it would be good. There's a lot of work we needed to do for the cost-based optimizations for GPUs. And then other side is currently I think we would love to do more work to do a better job for the data compressions inside during our ETL job inside the GPUs. So we are working on some of the GPU-based compressions, and we should also have very early work on the GPU-friendly compression format. And similarly, how you do the Lambda, operations on the GPUs. And then if you go beyond the Spark batch, what if we wanted to support the streaming operations, such as Spark streaming or the Apache Flink, Beam, all those stuff, right? And then on the other hand, if you think step back, so far our work has about to leverage our GPUs. Then what if you could leverage the, to step back, look into the data centers, right? And then, for example, Nvidia recently introduced a data processing unit. that will be enabled to offload some compression, the security, or the special operators on them from the CPU and the GPUs. So there's a lot of work we could do to enable this thing, to bring into a better future. So anyways, we have a lot of work to, in either in a vertical side or in the horizontal side. So I think we feel there's a lot of opportunities for, our talent to work on. And we will welcome the collaboration with the Rice Lab and Berkeley and many others. And on the other hand, if any of you, are interested to join us in Nvidia, whether, as an employee or the interns, we are always looking for talents. That's it.
Excellent. Thank you very much for the interesting talk. I guess you were scheduled for you to meet a few of the students and other researchers in one-on-one meetings now-ish. We could see if there's maybe time for a couple quick questions.
Sure.
Well, I think people have been asking questions in the chat.
Okay.
Yeah, so thank you again for the very interesting talk. I'm pretty excited. I was pretty interested in hearing more, both about Spark and, what's happening, in the COVID world, the COVID research world. So yeah, thank you again, I guess, one last time for coming and talking to us. And I hope we can hear some more exciting things in the future.
Thank you. Thanks for the opportunity to share. Thank you. Bye.
Thank you.